most learned session of the day. Let's move to the second session, which is going to be had by a very renowned personality, Dr. Snigdha Banerjee. But before she starts, I would like to take the privilege of giving her a brief introduction. Dr. Snigdha Banerjee is a professor in School of Statistics, Devi Ahilya Vishwavidyalaya, Indore. She was the head of the department from 2004 to 2013. At present, she is the chairperson, Board of Studies in Statistics, DAVP. She is also subject expert for other universities for BOS and reviewer of PhD theses from different states of India. She has received many awards in academics, research, and teaching. Like she was presented the AIAP Excellence Award by the Association of Inventory Academicians and Practitioners at International Conference in December 2018. She is also the recipient of the Research Appreciation Award by DAVB in 2017. She was honored by Gaurav Patra at Rajya Stariya Shikshavid Samman Samaroh in 2012. She was also awarded by MP Youngest Scientist Award in 1990. She received merit scholarship throughout her graduation and post-graduation. She has delivered plenary talks and chaired sessions at many international and national conferences and workshops. Her book, MS World, published by New Age Publishers and later by Lakshmi Publications, has been received well worldwide. She is the reviewer of 12 reputed international journals too. She has more than 50 research papers, including conference and presentations, 2 book chapters, and intellectual publications. Most of her papers are published in reputed journals. She, along with her team, has also developed a software package for a central government factory under the Ministry of Finance and provided consultancy services to national level finance company. She has guided 7 PhD and 7 MPhil scholars and more than 100 MSc projects in various areas of statistics, operation research, and management. She is a life member of Indian Society for Probability and Statistics, Association of Inventory Academicians and Practitioners, Senior Life Member of Operation Research Society of India, and Fellow Member of International Science Community Association. Her field of interest in research is operations research. At present, she is working on modeling and optimization of inventory models related supply chains. It's a great privilege to have you, ma'am, and I extend my warm welcome to you. Now, I would request you to please deliver your expert talk. Over to you, ma'am, please.
Thank you so much. Yeah, a very good afternoon to all the persons attending the meet. I would like to thank the organizers, DG Dr. Mr. Bhatnagar, head of the group of institutes, and also Dr. Raghubir, Dr. Namrata Kaushal, and Dr. Amit Jain for having given me this opportunity of sharing the platform with of sharing this platform. In fact, as was said on the first day, research is very important and research is data-based. Right. So when you talk about data and data-based research, finally, what do you do with the data? The data has to make sense. And for that, we have statistical tests.
Hello. Ma'am, you're not audible. Hello. Siddha ma'am, you're not audible. Hello.
दो मिनट मैडम, रूपाली मैडम 2 मिनट मैडम बात कर रहे हैं, अभी आ रहे हैं, 2 मिनट में ज्वाइन कर रहे हैं.
Okay. 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 Sir.
आपका माइक अनम्यूट कीजिएगा प्लीज.
Right. All right. I hope you can see. I'm sorry for the disturbance. This test of statistical hypothesis is part of statistics, statistical inference, as we call it. Okay, so there's some background which is expected from the about basic statistics from the person, because this is just a 1-hour lecture and not a lot can be covered. Especially, I would like the participants to know what is a normal distribution, what is a random sampling, and sampling distributions. And of course, we are going to cover the need for statistical techniques for research, statistical inference, the test procedure, various notations, hypothesis, types of hypothesis, how you can form the hypothesis, basic types of errors, and the probabilities. And then we would have hands-on sessions for chi-square tests, t-test, z-test, f-test, etc. So right now we are in a webinar because there is coronavirus infection and most of us are sort of safe at home. Now, because of COVID, a lot of research has got impetus. People are trying to find out what are the vaccines, medicines, causal factors, etc. And what would be the precautionary measures, what is the market scenario, what would be the preventive measures, etc. So suppose we have a marketing company, and suppose we have a pharmaceutical company, and they are trying to develop some market. Okay, we have a pharmaceutical company involved in manufacturing medicines. They are contemplating manufacturing a new medicine. Now they would be asking themselves the question, should we manufacture the vaccine or drug or should we not? If yes, then what should be the quantity? What should be the price?
This conference will now be recorded.
Across the supply chain. That means not just at the point of sales, but also at every point, starting from the raw materials, etc., to the wholesaler, to the retailer. The decision makers of the R&D of the company, they need to check the following before answering the above questions. The R&D team should see whether the vaccine drug is effective. Is it more effective than the one already in the market? The production managers should try and find out how much, what quantity we should manufacture. Then the marketing manager should try to find out whether they would have sufficient demand at these prices. Now, good decisions and research conclusions are always data driven. Data, big or small, would require finding facts out of it, extracting information out of it. Let us take a very simple example of COVID-19. Supposing you're trying to find out who is more prone to become infected Is it males or is it females? In fact, many of you would have read reports that males are more prone to be infected. Now, suppose some researcher tries to take a sample, a very large sample. He has taken 1,200 persons infected by COVID, and he has collected the data who are male, how many are females across the age groups. When you see this particular table, you can see that out of 1,200, 860 infected are men and 340 infected are women, forgetting, of course, about the age groups. Now, does this corroborate the claim that males are more prone? Let's take a little bit more detailed view of this. We are still taking males and females. We are still taking across age groups, but we are taking another factor, that is the amount of the level of exposure they have. Commonly, I think nowadays, females are taking care of the household chores because the maids are not coming, and males are going out and being exposed to the other COVID infected persons. So you can see that males are having a high exposure rate, that is 600. 600 out of the 840 males, 860 males are highly exposed. 160 have a medium exposure and 100 have a low exposure, whereas for females, 240 have a low exposure and the remaining 50 have high and medium exposure. So naturally, because of low exposure, you have less women in the earlier in this slide. So when you do research, you have to take care of many factors before you go on to collecting data. Right. So let's look at why we require statistics. Variation, systematic, and unexplained. This is essentially where we will try to distinguish. Whenever you go out to real life, outside the entire set of laboratory kind of experiments where everything is very well controlled, we come across variation. Even within laboratory, we come across variation. The two different guinea pigs would be responding differently to a medicine. However, when you go out to real life, you really see the variation, and we can always, we can always bifurcate the variation into two parts. One is systematic variation, and the other, systematic variation, is a variation which you can attribute to a certain cause. This variation is because of this cause. Whereas there could be remaining variation which we cannot explain, which is unexplained, random, or error, or what we say that this variation has occurred by chance. Supposing we talk about weights of persons. Now you will say that weight will depend upon the gender. Okay, so I take only males. You will say weight will depend upon the age. Yes, so I take age greater than equal to 25. If you say after middle ages, the weight increases, then you can take 25 to 30 here. And then you will also say that weight depends on the height, definitely. So I'll say I fix the height somewhere around 5 feet 7 inches. Now, having fixed all these, do you think we will get every person who's satisfying these criteria as having the same weight? No, I would possibly get persons with weights 58 kg, 63 kg, 74.5 kgs, etc., etc. But we cannot attribute directly these weights to something. This is the unexplained or random error which is bound to be there. Now, the systematic variation is what we put into the mathematical model when we do modeling. The unexplained variation is called the model variability or chance variation. Statistical techniques are required for modeling unexplained or random variations or errors. For these, you require probabilistic models and statistical analysis. And for tests of statistical hypothesis, what you require is samples from the data. Sample data will be used to arrive at valid inferences about the population. This is basically what we do in statistical inference in tests of hypothesis, and this is a very big contribution of statistics to research. Now I said we take a sample. Why take a sample? Number one, because if you study too many things, you're bound to spend a lot of money and time. So if you take a smaller subset, which we call as a sample, that is more economical. You'll spend less money, less time, and also you'll be able to do much more detailed and accurate study. However, at times sampling is essential, especially when the testing is destructive. Now, supposing some doctor tells me that I should have a pathological blood test for some random check, he has advised me that. Now, suppose the pathologist does not believe in sampling. He says, no, sample is not sufficient. I get only a part of your blood. I'll take the entire population. That means he's saying that he'll take out all my blood just for a simple pathological testing. Okay, fine, he may be right, but by the time I get the reports of my blood test, I may not remain in this world, possibly. So, statistics at times require samples for many reasons, as I explained. Now, how to make sense of data? There are two roles of statistics. As I said, big data, small data, all types of data require statistical analysis. Some more, some less. So there are two roles of statistics basically. One is called descriptive statistics and the other is called statistical inference or inductive statistics. Now, descriptive statistics is something which all of you must be doing. You intelligently collect. Intelligently collect means you can remember the first two COVID tables I explained to you. The data has to be collected intelligently, not just any data. Then you summarize it, you present the collected data, and this will be done, present the collected data as tables, as figures, only this collected data. Such analysis is what we call as exploratory data analysis, EDA. Now, the other part of statistics is also very important. This constitutes two parts. One is what we call as test of statistical hypothesis, which forms confirmatory data analysis. The other part is estimation. If you know nothing about the population, you estimate, and this is again exploratory data analysis. Since we are talking about tests of statistical hypothesis in this talk, we talk a little bit more about tests of statistical hypothesis. We have two types of tests. One, if the population distribution is normal, then you talk about parametric tests. But what happens if the population distribution is not normal? If it is not normal, we use what are known as non-parametric tests. For example, if the data is nominal, that means you're talking only in terms of names. Let's say names of countries with the number of persons infected with COVID. This is nominal data. You just have names and the counts of frequencies against those names. Or ordinal, where you can order the data. That means I think India now has the 7th rank in COVID number of infected. So when you can order the data, that is called ordinal data. Or when you have quantitative data, let's say ratio, scale, etc., ratio, interval, then you have quantitative data. But if the population had been normally distributed, we would have applied parametric tests. But the population is not normally distributed, then you go on to non-parametric tests. Today we'll take up parametric tests mostly and some non-parametric tests like the Chi-square test, etc. Now let's go back to the technique. Essentially, what research question do you have? You have the research question regarding the entire population. Population means the entire set of units. Maybe it is number of persons, maybe it is some items, maybe it is human beings, or maybe animals or guinea pigs. This entire set is called the population in which you are interested. Supposing I say I'm interested in how much this particular group of persons who has joined here is learning, then this is my population. If I say that how many of those who were actually awake during my lecture has learned, then that becomes my population. Okay, so I have an entire population. This has a lot of points, a lot of items. Now from this, I can say take some subsets, and those subsets are called samples. Those subsets are called samples. Now supposing I draw a sample from here, and which we call as a random sample. Now what is random sample? Random sample is a sample which is sampling a sample taken using a technique such that each of the samples has the same chance of being selected. So I have a sample. Now what do I do with the sample? I get some data from the sample, and based on this data, if I make a calculation, for example, I draw a sample mean or a sample variance, or let's say a t-statistic. That is called a statistic. And when you use a statistic, a function of the sample observations, for testing, it becomes a test statistic. Now we have calculations based on the sample, which we call as the test statistic, and then that is used to answer the question regarding the population, and the question goes off, we have the answer. So population, random sample from the population, calculate from the sample population, from the sample data, and answer the question regarding the population. So this is the basic, and although test of statistical hypothesis is sort of people say it's confusing, I try to put it as simply as possible so that after this lecture is over, you can say, okay, I know something about it. So we will be talking about the main concepts, null and alternative hypothesis, how to state them, the two types of errors, their probabilities, interpretation, p-value approach, and well, idea of critical region I will not take, choice of the test, how to choose which test to use under which situation. Right. So why should we test, and what is the test? As researchers, most of you are doing research or using research, you know that there are many occasions when a researcher has an idea or assumption or assertion regarding the population. You might want to prove that a medicine, a person from some researcher from pharmacy may try to prove that his medicine is better than the earlier medicines. For example, recently, I think just 4-5 days back, there was a report from Tundla that some homeopathic doctors, pardon? Some homeopathic doctors have combined homeopathic medicines with the routine medicines. They divided the sample into 2 parts, and they found that when they used the homeopathic medicines, the persons showed negative corona effect within 3 to 4 days as compared to the others who took some weeks before they showed negative effects. So they were trying to show using a sample that their medicines could be more effective.
Zoom में जब सीएम मैडम का फोन आता है तो Zoom में हमेशा क्या होता है, म्यूट हो जाता है. ये म्यूट ही नहीं हो रहा है, बता तू.
So this idea which you have is called a hypothesis. However, if you have the idea, who's going to believe your idea? This idea is called a hypothesis. However, who's going to believe your idea? This idea needs to be checked or tested. That means you have to give evidence that yes, your idea is actually true. So for that, what do you have to do? You have to collect data from a representative sample of the population. And then you apply the test of hypothesis. What is the test of hypothesis? The stepwise procedure for answering the question whether to accept or reject the hypothesis, which is based on concepts of probability. Now, the big question is, does the data support the claim or hypothesis? This is the only question that we are trying to answer in our tests of statistical hypothesis. Of course, there are a lot of variations, but please remember, just like in a court, you say that the evidence is what will decide the final decision of the judge. The judge will base his decision on the evidence. Similarly, your decision as a statistician, as a decision maker, will depend upon the data. If the data supports the claim, you will accept it. If it does not, then you reject the hypothesis. So as I said, I'll put things very simply. So steps in hypothesis testing procedure. Step 1, you have to state your hypothesis, null hypothesis, and the alternative hypothesis. We will go into details in the next few slides. Right. So in the next few slides, we'll see what these are. Then you have to select the appropriate statistical test. The statistical test would depend upon the type of data that you have. As I said, you might have nominal or ordinal or normally distributed or not normally distributed data. So that will decide upon the test and the question which you are asking. Are you asking a question about the mean, about the goodness of it, etc.? That will decide upon the appropriate statistical test. Then you decide upon the what we call as level of significance. That is the level of mistake in your decision that you're ready to tolerate. Then after all this, don't begin collecting the data at the very beginning. Now you start collecting the data from the sample. You compute the observed test statistic. For that observed test statistic, you find the p-value. The statistical softwares will help us in finding the p-value. And once you have the p-value, after that, depending upon the p-value, you accept or reject the null hypothesis. And please don't leave at that. Once you accept or reject the null hypothesis, that this would be a technical language. After that, you put your conclusions in the language of your question, of the question which you asked or the researcher asked. You translate it into that particular language. That will end your research. So what is a null hypothesis? We denote it by H0. This states the assumption which is to be put into numerical format. This states the question to be tested. For example, supposing we are all teachers, supposing I say that the grade point of average of juniors, my MSc first year students, is at least 3 on a point of 5. That means I'm saying mu generally stands for the population average. So the average grade point of the students is greater than or equal to 3. So I have to have a numerical value. And when I begin the test, I begin with the assumption that the null hypothesis is true. I'm not saying we always accept it. You may accept, you may not accept. But similar to the notion of innocent till proven by a judge, the judge always assumes the convict to be innocent. And if the evidence is heavily against the convict, then he says that, okay, this person is guilty. Similarly, you begin with the assumption that the null hypothesis is true, and then try to test whether it is true based on, the judge based it on the evidence, and we will base it on the data, which is the supporting evidence for us. Now, what is the alternative hypothesis? I think most of you call it what is known as research hypothesis. You take your research hypothesis and please do not call it the null hypothesis. You call it the alternative hypothesis, which is denoted by H1 or HA. It is the opposite of the null hypothesis. For example, my null hypothesis was the grade point average is at least 3. Opposite will be that the grade point average is less than 3, mu less than 3. Now, it's generally easier to form the alternative hypothesis first because you know what you want to prove, you know your research hypothesis. So put that as the alternative hypothesis. Whenever H0 is rejected, H1 is accepted. That is why I think most of the researchers are interested in rejecting the null hypothesis. You say my null hypothesis was rejected and you become very happy about it. So what we would do is generally first form the alternative hypothesis, which is your research hypothesis, and the negation of that would be the null hypothesis. Put that in terms of numericals, and I'll go back to the last slide and just try to remind you that equal to sign always present in the null hypothesis, never in the alternate. It could be equal to, it could be less than equal to, it could be greater than equal to, because when you test the hypothesis, you take the boundary value. We'll see how that is done later. Okay. Now, once again, when we talk about taking a sample and basing the, shall I stop? A lot of disturbances there. When you base your,
Please mute, all of you, please mute yourself, please. Shakuntala Chauhan, please mute yourself.
so
Please
when you're
continue.
basing your decisions, when you're basing your decisions on sample, but you are talking about population, you're concluding about the population. Naturally, I may have a good sample, I may have a bad sample. For example, if I took a sample of all the backbenchers, all the persons who do not study, and then examine their results and find the mean, I might get the grade point average as 2.5. And I'll reject the hypothesis that the grade point average is at least 3. But that was because it was by chance that I got a bad sample. But such things may happen in real life. So we realize, I think statistician in this sense is one of the very honest persons in the, in the research community, that we do accept that we can make errors, and we also quantify those errors. That is one reason why data scientists also require statistics, because the type of errors that can occur are two very major types. First of all, let us realize that there is some truth which is existing, but we do not know it. Nobody knows it. As we say, God knows. Okay, like the judge does not know who has committed a murder. This is not known to us. What we can do is, we can make a decision which is data-based. We can either reject the null hypothesis or not reject the null hypothesis. That means we reject the null hypothesis, accept the alternative. But what happens is, when you reject the null hypothesis, it may happen that that sample has come just by chance, even when the null hypothesis is true. But we have said that you reject the null hypothesis and we've committed an error. Alternatively, the null hypothesis may be false and we are not rejecting it. Once again, an error, because H1 is true and we are not rejecting null hypothesis, we are accepting null hypothesis. This is called type 2 error. And then there are some familiar terms that, some terms with which you're very familiar. One is alpha. This is the probability of type 1 error. That means you are rejecting the probability that you're rejecting the null hypothesis when it is true. And 100 into alpha, this is called the level of significance. And we fixed this initially, that we are prepared to tolerate only this much error of type 1 and no more. About type 2 error, yes, this is also important. And the probability of type 2 error is called beta. And this is also important in power analysis and deciding upon the size of the test. And when you fix the type 1 error, alpha, you try to maximize the power of the test, which is 1 minus beta. So I hope you've understood alpha and beta, probability of type 1 error, probability of type 2 error. Right, and generally we fix alpha at less than equal to 0.05 or 0.01. These are the conventions. You can be more lenient. You can put it as 0.1 or something, and you try to minimize beta. The convention is that beta should be less than 0.2. Now, okay, you've collected the data. How to arrive at your decision? When to reject H0 and when to not reject H0. We calculate the observed value. We keep saying observed value. What is the observed value? It is the value of sample statistics, the function of sample observations calculated from the observed data. For example, if I calculated from that backbenchers sample, I got the GPA as 2.5. Now, after that, once we've got that observed value, we find out the p-value. What is the p-value? That is the chance of getting that observed value or more extreme value, a value which is more towards the alternative hypothesis, when H naught is true. The probability depends on which hypothesis is true, whether H naught is true or H1 is true. So p-value is the probability if H naught is true. Okay. And if p is very small, that means if the chance of getting the observed value when H naught is true is very small, it is highly unlikely that the null hypothesis is true. And so what would be your decision? The data, we say that the data does not support H naught, and that is all the evidence that we have. And so the decision would be to reject the null hypothesis. So when p-value is small, less than equal to 0.05, you reject the null hypothesis at 5% level of significance. If p-value is less than 0.01, you reject the null hypothesis at 1% level of significance. Now, how do we choose the appropriate test? Number one, we should look at the number of variables. Technique, I should replace possibly this word by test. If you have one variable, if you have two variables, then the scale of measurement, whether you have categorical data, whether you have quantitative data, whether the data are dependent, whether they are independent, whether they are related, the type of hypothesis, whether the hypothesis is regarding the population mean. Please remember, hypothesis is always regarding the population. So whether the hypothesis is regarding the population mean, difference of means, variance, independence of attributes, goodness of fit, etc., all this will decide upon the type of about the choice of the particular test. The sample size, especially when you're talking about quantitative data behaving as with population behaving in as normal distribution, the size also matters. When it is a large sample size, you can use a z-test, and when it is a small sample size, and your question is regarding the population mean, you use the t-test when the population variance is unknown. Now we've been talking a lot. Let's take up an example. You have, suppose there's an agriculture company which has developed some new method of cultivating soybean. It has applied that method, and it tries to find out whether the yield earlier, for the earlier 2 years, the yield was 520 bushels per acre. And they've taken a sample of 1 acre farms, the yields from 1 acre farms, and using this sample, they would like to prove that the amount of the yield has increased. Now, what do we do? First of all, we have to state the hypothesis, the null and the alternative. Which one will we state first? We are trying to show that the yield has increased from 520. So we will state our alternative hypothesis as our research hypothesis, that is the mean yield is greater than 520 bushels. What is the null hypothesis? It is the opposite of the alternative hypothesis, that is the yield is less than or equal to, the mean yield is less than or equal to 520 bushels. Note that the equality sign is in the null hypothesis. Next, what do? We go out and collect data. Say we collect data of 64 farms, random sample of 64 farms. Don't take only those ones which have good yields. That is not going to support the hypothesis. You take a random sample of 1 acre farms, and then you find the yields from there. You find the sample mean. Let's say the sample mean is 560. Does it? So does it mean that actually there's a big difference? 560 and 520 do not seem to be that different, isn't it? But I hope, I told you here that it is known that the population distribution is normal with standard deviation 50. So standard deviation is pretty large. And now what I will do is I'll apply what is known as a Z-score test, which is the observed value of the mean minus the the boundary value of the null hypothesis, that is 520. So 560 minus 520, in fact, this is divided by standard deviation upon under root of 64, which is 8. So divided by 50 upon 8, that is multiplied by 8 into 50. And I get the value 3.2. And the corresponding p-value is 0.00068. Definitely, you can see that this is less than 0.01. So what should be my decision? My decision would be reject the null hypothesis. That means we are saying that it is very unlikely, such a value 560 is highly unlikely to be observed if mu is less than or equal to 520. So we will say that the new method of cultivating soybean has been successful. So we go back to our earlier slides. So we will see how to find p-value directly. In fact, as I said, we have some hands-on sessions, and we will see how to apply the chi-square test for categorical data. Most of the persons from management who are doing research in management have huge data, but mostly counts of data, frequency data. So they will use categorical data, chi-square test. Then we use the Z or the normal scores test for means, t-test for single mean, paired samples, two independent samples, and how to choose the test. I think we'll fall slightly short of tests, so I'll skip some of these. Now, test for categorical data, chi-square test is used when the data is in terms of a contingency table, what you call as crosstabs. That means you have rows and columns, and those rows and columns, the data is in terms of counts or frequencies. And the general formula which you use, as we had in those first two tables. So general formula that you use is observed OI minus EI whole square upon EI, and the summation of that, that is the sum of all the differences squared divided by the expected value. But let me tell you one mistake which people mostly make is apply this even when you have values. What you need to do is you should apply this only to frequency data. Observed frequency minus expected frequency upon expected frequency. Okay, the square upon expected frequency, and then take the sum over all the cells of the contingency table. All right. So now let us go to some of the tests for contingency tables, but the conditions for validity are that the total frequency should be high and the expected frequency in any cell should be greater than or equal to 5. Let's go to an actual example. What's the test? Okay, so let me take an example of chi-square test for independence. This problem you must have come across somewhere, possibly. Public opinion or some such similar problem might have arisen in your research. Public opinion poll surveyed a simple random sample. Random is important, otherwise your test will not be valid. Sample of 1,000 voters, a large number which satisfies our condition. Respondents were classified by gender, males and females, and by voting preferences, Republican, Democrat, or Independent. And the results are shown in this table. You can see that this is the actual data. This yellow set is the actual data provided. You have voting preferences, Democrats, Independents, total in fact, this is possibly Democrats. Okay, this is Republican, this is Democrats, this is Independent. And males and females. That means 200 males voted for the Republicans, but 250 females voted for the Republicans, and so on and so forth. So this is the data given to me. What we would do first is we calculate the totals. This you can see in the formula box. I just said equal to sum of this. The address of this cell is C8. The address of this cell is D8. So I said sum C8, sorry, E8. This 1, 2, 3. Okay. C8, D8, and E8. So I say sum C8 to E8 equal to sum C8 to D8, and I got this value. Similarly, if I say equal to, this sign is important, equal to sum C9, D9, E9. So I say sum C9 colon E9, and I got this value. So we take the marginal total. Similarly here, I said sum of C8 and C9, sum C8 to C9, I got this value, and similarly. Now, how do we find the expected frequency? For that, we assume that the null hypothesis is true. Now, we did not formulate any of the hypotheses, did we? No, we did not. So, what is the null hypothesis? The null hypothesis is the opposite of the research hypothesis. Possibly that gentleman, whoever has formulated this, whoever has done this data collection, wanted to show that voting patterns is dependent on the gender of voter. So this would be his research hypothesis or our alternative hypothesis. Whereas opposite of that would be H0, the null hypothesis, that is the voting pattern is independent of the gender of the voter. Now, if null hypothesis is true, what will happen? Irrespective of the gender, this is the total vote for Republicans, for Democrats, for Independents. Okay. And this is the last line. You see the total votes for each party. In that line, I have 450, 450, 100. So irrespective of the gender, this is my total vote for Republicans, 450. Irrespective of the party, this is my total votes for males. So had these been independent, I would expect that the number of males who have voted for Republicans would be 400 into 450 divided by the total frequency, that is 1000. This is what I've written in this cell, if you can see. So all I've done here is, you can see, multiply the cell F8, this is F, this is 8, F8, this value by the value C10 and divided by this 1000, that is F value in the cell F11, F10. So this is how I get this expected frequency. Similarly, I get this expected frequency by multiplying this cell with total 450 by 400 and dividing by 1000. I get this cell frequency 40, expected cell frequency 40 by multiplying 400 by 100. 400 by 100 and dividing by 1000. So this yellow set is my set of expected frequencies. This is the set of observed frequencies. And then what do I do? All that I need to do is just type something. You can see here, I have said chi-test, CHITEST, and then within a bracket, I have said C8 to E9. What is C8 to E9? This is my observed range, this upper yellow set of values from 200 to 50. And comma, and please remember this should be an equal to sign initially. Then the next set is the observed frequencies. I have from C15 to E16, that is 180, 180, 40, 270, 270, 60. And that is all I do. And I click, I just have to enter a right sign, correct. So this is what I do if you want, and I get the value P. This is, I've already written the formula here. If I enter this formula, if I want to have my values in this cell, all I do is put an equal to sign, and then I say CHI, I automatically get a, it is saying actual range, so I'll just select the actual range. I got the same thing, and then comma, I select the expected range. Here, this is the expected range, and I close my bracket and just click on this right. Okay, I get the same value. So it's as simple as this. In fact, I would suggest most of you to use R, because that is the programming language which is in, but because I had to show this online, so I chose Excel. So this is the P value that you get. And now all that you have to do is accept or reject it. Not based on what? Based on whether P value is smaller than 0.01 or not. Yes, this is much, much smaller than 0.01. So what should be our decision? Decision is to reject the null hypothesis. And what is the conclusion? We conclude from the using the wordings of the question. So our conclusion when we write in our research paper would be that we conclude that voting preference is independent of the gender. All right. So let me go back now to the right. Now, this is the Excel syntax: actual range, expected range, and the probability. Chi-test gives us this probability. Now, chi-square test, for goodness of it, is very important because many times you want to see whether population has a certain distribution. So here, the null hypothesis is that the data are consistent with the distribution which has been specified by the researcher, and the alternative hypothesis is that the data is not consistent with a specified distribution. So for example, supposing we have this problem: some toys company prints baseball cards, and the company claims that 30% of the cards are rookies, 60% of the cards which it has printed are veterans, some names given by the company, and 10% are all-stars. And the cards are sold in packages of 100. So supposing we take one package and a randomly selected package is taken, and we try to find out how many rookies, how many veterans, etc. are there, and we find that there are 50 rookies, 45 veterans, and 5 all-stars. But before that, please remember, we have to state the hypothesis. So the null hypothesis is that, how would you start stating? Alternative hypothesis, that at least one of the proportions in the null hypothesis is false. That means the person who has actually printed the cards is not stating the right thing. Those who are betting on those cards would say exactly this thing, that you've printed more of these cards or less of these cards. And what would be the null hypothesis? This is the proportion of rookies, veterans, and all-stars is what has been stated: 30%, 60%, and 10% respectively. Now, we have to formulate an analysis plan. Because this is categorical data giving you frequencies or percentages, we have to use the chi-square test, of goodness of it. And you have to find out the degrees of freedom. The degrees of freedom is generally the number of rows -1 into number of columns -1. So let us go to the same problem I've written here, and the same null hypothesis and the same alternative hypothesis has been written here. And this is what we have: the observed data, 50, 45, and 5 for rookies, veterans, and all-stars. And the expected frequencies, because the expected probabilities are 3 out of 10, 6 out of 10, and 1 out of 30 out of 100, 60 out of 100, 10 out of 100. What would be the expected number when you take 100? 0.3 into 100, that is 30. 0.6 into 100, that is 60. 0.1 into 100, that is 10. So these are my expected frequencies provided my null hypothesis is true. This is where the null hypothesis comes into picture. As we said, we always assume that the null hypothesis is true. So we have the observed range, we have the expected range, and what do? We try to find the probability. This is the syntax for my probability, and this is what I obtain using this syntax, Kitex G28. You can see this is G26, G27, G28. So G26 to G28 is my observed set of values, and F26 to F28, this is my expected set of frequencies. And then I just had to click on this and I got this as the p-value. So here the p-value is very small once again, and we reject the null hypothesis. Our decision is reject H0, and hence we conclude that the person who has printed the cards is actually not speaking the truth. But once again, this is at, we have a small chance. What is that small chance? That is the p-value 0.00005. That means this much chance that we may be wrong in making this decision that the person has not printed the cards properly. So this is the chance that we may be wrong when we are rejecting the null hypothesis. All right, so now we move on to quantitative data and find out which parametric test is to be applied. We have done with non-parametric, or what we call as distribution-free test. Chi-square test was a distribution-free test. So test for means when the variance is known or the sample is large. In either case, you apply what is known as Z or normal test. By large sample, I mean more than 30 observations. More than 30 is the sample size. When the variance is unknown and the sample is not very large, then you apply what is known as t-test. If you have two samples, independent samples, you apply the independent samples test. When you have samples which are related, for example, before or after, before you take a test before giving a certain coaching and after giving a certain coaching, and you compare the scores for the same person, then that data becomes paired samples. So you have paired samples, t-test, etc. When you're testing for equality of means and you have more than two populations, you use what is known as analysis of variance. Then when you have test for variance, you apply a single sample chi-square test, etc. Similarly, for proportions, you can apply the Z normal scores test. And for validity of these tests, what is important is that the population distribution must be normal. Well, you cannot exactly get normal from the real life, but let's say it should not be far from normality. So let's briefly see what is a sampling, what is a norm, I mean, what are the concepts behind these tests. Number two, let me take first, that is normal distribution. When you say it is not far from normal, you just look at the what we call as the measures of skewness and kurtosis. Gamma 1 not very far from zero, gamma 1 close to zero, gamma 2 close to zero, and what we call as QQ plot should be almost a straight line. Then sampling distribution of a statistic is the distribution which we obtain by taking all possible samples, calculating the statistic from that, and then you draw a histogram from there and obtain a model of that particular distribution of the samples. That is called sampling distribution. And for large samples, we use what is known as central limit theorem, essentially, which says that for large samples, the sample mean has the sampling distribution of the sample means has a normal distribution with the same mean as the population, and variance, which is the population variance divided by the standard under root of the sample size. So let us take up some Z tests now. An insurance company is reviewing, let's take up this example, is reviewing the current policy rates. When originally setting the rates, they believed that average claim amount is $1,800. They're concerned that the true mean is actually higher than this. They're having higher claims and they could be possibly in a potential loss. What they did was they randomly selected 40 claims and calculated, they already have data for claims, they calculated a sample mean of $1,950, much higher than $1,800. But that also depends upon the variance of the population. Assuming that the standard deviation of the claims is $500, square root of variance is $500, they set 0.05 as alpha. That means they are prepared to tolerate 5 out of 100 error. Error in 5 claims out of 100 when they make their decision. So first step, set the null and alternative hypothesis. Null hypothesis is that the claim is less than or equal to, average claim is less than or equal to 1800. Opposite of that is the alternative hypothesis. The claim is greater than 1800, which they are worried about. They're trying to show that it is actually this much. And step 2 is calculate the test statistic. This is the formula for the test statistic. This is the sample mean. The sample mean turns out to be 1950. And the mean from the null hypothesis, the boundary of the null hypothesis, that is 1800 divided by the sample standard deviation, that is 500, upon square root of the sample size. Sample size is 40. They took a sample of 40 claims. So we calculate this. The calculated value, observed value of the test statistic is 1.897. This we could have done in Excel as well. And now we can directly find the probability from Excel. What probability do we need to find? If it is high, the sample supports the alternative. So when do we reject the null hypothesis? When mean is high. So you reject the null hypothesis when the probability of having a Z score is greater than the calculated value. And this is the level of significance. And very interestingly, for this problem, the p-value turns out to be 0.028. Now, this value is less than 0.05 and greater than 0.01. So what do we conclude? As stated by the company, it is ready to tolerate error in 5 out of 100 decisions. So at 5% level of significance, we can very easily reject H0. But if the company had been more stringent, had they said that we'll tolerate error only in 1 out of 100 cases, then we cannot reject null hypothesis. Such a difference might have occurred by chance. And we would have said that there is no evidence against H0, but right now alpha is 0.05. So we reject H0 at 5% level of significance. Now, this also brings us to a very interesting thing, that is, you must have heard of one-tail test and two-tail test. Here, we are rejecting the null hypothesis when you have higher values. That means we say the critical region is on the right tail. And the area under this critical region is what we call as alpha. So alpha is this area. Critical region, that is the set of values, if you arrive at those values, you reject the null hypothesis, is this. And if the value would have fallen here, had it been something like 1810, the value of Z would have fallen here and we would have accepted the null hypothesis. Now you also have one-tail test on the when we reject on the left-hand side. For example, well, I think I'll fall short of time, so I would move on to t-tests. I'll just skip some of these. We could have two-tail test, that is, we reject when it depends on the alternative hypothesis. Here, the alternative is mu less than 30. So I'm rejecting the values on the lower tail. So I have one tail, lower tail test. Similarly, here, My alternative does not have any direction. The person who has framed the null hypothesis has no idea about to which direction the in which direction the difference might occur. So we use what is a two-tailed test. That is, if it is too large, we reject the null hypothesis. If it is too small, we reject the null hypothesis. All right. So I'll just ask the organizers if I can continue or should I stop here? Hello. Do I have the permission to continue? All right.
Hello.
Hello. Can I continue or should I stop?
Ma'am, you have last 5 minutes.
5 minutes. Okay, fine.
Yeah, ma'am.
So, okay, fine. So, the most common hypothesis tests are one sample t-test, two sample t-tests for independent samples, two sample t-tests for paired samples. So let's take these one by one. And the syntax for two sample t-tests is t-test, array 1, array 2, number of tails, one-tailed or two-tailed. We just saw that if the alternative hypothesis is showing just one direction, then we use one-tailed test, and otherwise we use two-tailed test. So one-tailed you write one here, two-tailed you write two here. Now the types they have defined in Excel. If you use one-tailed test, the type is 1 for paired t-test, 2 if you have paired t-test and you're sure that there will be equal variances, and 3 for unequal variances. And then let's go, and the syntax is t-test, array 1, array 2, tails and type. I think I'll go to two sample tests, t-test for paired samples. Suppose I have this problem. 15 women participated in an 8-week weight reduction program. Their initial and final weights were measured and are presented in this table, following table. They would like to find whether the weight reduction program was effective at 5% level of significance. In order to do this, what they did was they took sample of 15 women before the program and after the program. They took the weights of the women before the program and after the program. You can see the differences. This is the basic data provided. You can see the differences, and if I find the mean difference, which I just used average of this set, then I got 5.2. Looks like some difference has been there. Let's now directly calculate the test statistic. And how do? You can see the syntax here as well as here. I said t-test C19 to C33 for the first set, D19 to D33 for the second set. And I needed, what kind of hypothesis do I have? Once again, I'm going back to the hypothesis. I assume by now you know that we must state the null and alternative first. So mean of the pretest, mean weight of pretest is the same as mean weight of post-test. This is the null hypothesis. And what our research hypothesis is that initial weight is significantly larger than the mean weight after the program. So our p-value is so many zeros and 882. That means the value is less than 0.01. And what is the decision? You reject the null hypothesis at 1% level of significance, and hence we conclude at 5%, 1%, whatever level of significance, that the weight reduction program was successful, right? So if you want, we can go to the t-test for unrelated samples. People have studied flexibility of gymnasts, and 15 gymnasts, 16 athletes were measured by some method, sit and reach method. And this is the data given to us. These 15 gymnasts and 16 athletes, these are the flexibilities calculated. And then we assume t-test with equal variances, and we just put equal, we just type in this formula bar equal to t-test and the range for the first one, B18 to B32, the range for the second one, C18 to C33. And then I want a two-tailed test. Why do I want a two-tailed test? Because they're just talking about difference, not about the direction of the difference. This is more flexible, this is less flexible. No. So I'm taking a two-tailed test, and 2 because this is for independent samples, and this is the calculation. This is the p-value. And what do? We will, now the question is for you, and with this question I leave you, and I hope that you have been able to understand some things. Thank you for your kind attention, for whoever stayed till the end. And the test of statistical hypothesis basically is related to model building, testing, interpretation, and finally, it gives you guidance for the next step. This is not the end. This is the beginning, in fact, for your innovative research. Thanks to the audience. Thanks to the organizers.
Thank you so much, ma'am. That was a really wonderful presentation, and I'm really sure that it will really helpful for the participants. Now it's our the doubt clearance sessions. If participants having any query or the questions regarding the presentation, they may put their questions and query on chat box only. And for this, I'm handovering to the Neena ma'am. Neena ma'am, please over to you. Handle the chat box.
Yeah, thank you, Rupali. And thank you so much, ma'am, for your informative session. And definitely we have got one query here. She is Shubhi Khare, a participant, and she wants to ask that how to identify variable at the time of doing research work if researcher is using secondary data.
If the researcher is using secondary data, well, don't begin with the data. Whenever you do research, you always begin with your research question. You should identify what you want, what is the question that you want to answer. And then you will automatically get the variable of consideration. The variable doesn't come from itself, it comes from you, from your research question. What is the question you are asking about the population? For you should find out what is the population, what is the question that you want to answer, and then identify the variable. Okay?
Okay, ma'am. Thank you. And there is one more question from Dr. Jyoti Gupta. Ma'am, please explain the difference among students, t-test, ANOVA, and linear regression.
Okay. Well, students, t-test, and ANOVA, I would say it depends on the number of samples. If you have 2 samples, you will use t-test. If you have more than 2 samples, you will use ANOVA. For test of equality of means, both of them are for test of equality of means. One is for 2 samples, this will be t-test. For more than 2 samples, this would be ANOVA. The underlying assumptions remaining the same, that is, the population is normal, error population is normal, and homoscedastic, that means the variances are the same. Now, when you talk about regression, regression is altogether a different technique. Although we use regression, we do use what is known as the amount of variation explained by the model that sometimes is brought into the regression arena. But basically, regression is for predicting the output value based on the input value. That is, if you have an x-ray, for example, if you have the heights, that's your x variable, and weights is what you want to predict from height, you will have a model, and from that model you can predict. So regression technique is generally used for this kind of prediction. But tests for equality of means generally would not come from these. Students t-test and ANOVA both are for tests of equality of means. I hope I could make you understand. You may ask further questions, or you can write to me on my email ID.
Okay.
If you want, I can type it out for you. Should I?
Sure, ma'am. That will be very helpful for the participants.
Yeah. My email ID is B, not capital, BANS, caps lock is on. Small, this is all small case. I don't know why it's coming in capital here. Simply because of the font that I've used there. BANS, right now it's coming, BANS_1 @rediffmail.com, and in the subject line, please write the reference of this. This is my mail ID, BANS_1 @rediffmail.com.
Okay, ma'am. Thank you so
So
much.
in
In
case
fact,
anybody has any problem, rediffmail.com, I forgot to write that possibly. So
okay.
right, and I'll be very happy to get connected with anyone who has any queries.
Right, ma'am. So we'll send the rest of the question through mail.
Pick your part.
Shall we send rest of the question through mail?
Yeah, they can individually write to me. They can individually write to me, no problems.
Okay,
The
ma'am.
participants can,
Thanks.
are there any
Yes,
questions or?
Yes, ma'am. There is one more question from YouTube chat.
Okay,
Shall I?
if you have, sure.
Right, ma'am. This is from Dr. Satish Kumar Singh. The question is, there is always a question in researchers' mind that what should be actual sample size in bracket practically if he is doing a research in management or social science.
Right. I think around 250 should be okay, unless it depends upon the variability. As I said, those power, etc. When I was talking about power, that helps us in finding the sample size. And the sample size depends on the effect size that you want to identify, that you want to catch through your test, and also on the variability, because in social sciences and management you have a lot of variation, so you need slightly larger samples. I would say around 500 should be okay. But definitely it will depend upon the variability, that means the variance, standard deviation of the population that you're dealing with. For that, you have to take a what you call as the pilot survey, and based on the values from the pilot survey, you come back here. So because of the huge variability, especially in management and social sciences, I would say 250 to 500, but 500 would be better because of the variability. If there's less variation, you can come on around to 250.
All right, ma'am. Thank you so much for your valuable inputs. And over to Rupali.
Okay.
Thank you.
Thank you so much, Nia ma'am. Thanks a lot. Thank you, ma'am, for answering all the queries and questions. Here the day second is over. Hope that all the sessions were also very enlightening for all the faculty participants. I really thanks for their valuable presence and patience listening. Thank you, faculty. And just a reminder, please fill and submit the feedback form of these sessions too. We will meet you tomorrow at 10:45 AM. Till then, bye and take care. Thank you, Nilesh sir, for your technical supports. Participant, you may leave the meeting now. Thank you so much. Thank you, ma'am.
Rupali, let me correct. Tomorrow's session will be start at 10 AM.
Okay, sorry.